Integrability, Engage and String Theory 2024. So, welcome. So, as you see, we are in São Paulo, in Brazil. So, it's a pleasure to have the first meeting of IGST in South America and the second IGST outside Europe. So, it's a great pleasure. So, we did it once during COVID, but no one wants to think about it. So, it was great fun, but it's for sure going to be much better this time with everyone in person. So welcome, everyone. So I have a few things that I want to say. Very important thing. If you are a speaker, send us the PDF. So that's related to, we want to make sure the conference goes smoothly. We are trying something new. We will have this mixed format. We asked all the speakers, do you prefer to give Blackboard or slides? Slides are more formal, but then you have 30 minutes. And Blackboard is more chill, and you have 45, and you choose whichever one you want. But for this to work well, we need all the PDFs with the tech people. So do send us the PDFs before the day of your talk, as soon as possible. Tomorrow there will be the conference dinner. For lunch, we are preparing some recommendations we will put on the website. But basically, there are many locals here. You can follow some of us. My main recommendations will be the shopping mall and the particular place we went last week for those that were here last week. If you want more affordable recommendations, in Rua Itapeva, there is some cheap buffet place that you can eat for 20 reais. That's very affordable. And we are going to prepare a website with those recommendations that will be online in a few minutes. It's a big city, so especially at night, and depending where you walk, don't carry your phone like this, looking for Google Maps. If you do, it's very likely a small kid with a bike will pass and take the phone. So that I've seen several times in Paulista, bicycles going around, waiting for an idiot to be, and the phone goes. So just don't do it. If people are taking out the phone, then it's okay, take out the phone. Otherwise, just be reasonably street smart and everything is totally fine. Posters will be in the coffee break area. And so at the break, you can already put the poster. And yeah, so that's it. So I would like to thank very much the Instituto Principia, which is where we are having this conference. The talks will be here in the morning, and then in the afternoon we'll go to the building in front where people can discuss and so on after the talks. And of course to ICTP-SAIFR, who is hosting this event as a partnership with Instituto Principia. So welcome everyone, and let's try to be on time. So it's a great pleasure to have Simon give us the opening slide talk of the conference.
Thank you so much. All right, so let me start by thanking the organizers for giving me an opportunity to present some of the work I've been doing together with Nikolai Gromov and with Paul Ryan. So in this conference, I don't think I need to motivate why we should look at n equals to 4. Neither do I have to tell you that integrability has been very powerful in finding the spectrum of n equals to 4. Nevertheless, let me start with a remarkable statement, which is that integrability is actually present for all values of the coupling. But just because we have integrability, both in the strong coupling and in the weak coupling regime, doesn't necessarily mean that we understand them equally well. Rather, right now, we're lacking strong and efficient tools to attack the strong coupling regime. So how do we try to change this unsatisfactory state of affairs? Well, today I will be using one of the most powerful integrability technique that we have developed so far. And that technique is the quantum spectral curve. So I will try to use the quantum spectral curve to see how much we can learn about the strong coupling regime. Now, for those of you who are not familiar with the QSE, let us just briefly recall the current state of the QSE. So at weak coupling, we have by now amazing analytical control. And we have amazing analytical control because we have an algorithm in which you can give me the quantum numbers, or rather you can give the algorithm developed by Dima and Christian the quantum numbers, and it will spit you out the anomalous dimensions. If you go to strong coupling, we lack such an algorithm. Instead, we will have to rely on numerics. Now, we have done very good progress using numerics, but nevertheless, numerics will become increasingly slow as we increase the coupling. And numerics will, in the end, only produce numbers for us. It will be very hard to learn about the analytic structure of the strong coupling spectrum using only numerics. Some benchmark results have been found. A typical number to give is the Konishi operator, which I've written down here. But let me still emphasize that for most states, we do not know how to treat this problem. So in this talk, I will introduce a new approach to the QSC. And the main power of this new approach is that it is strong coupling friendly. And I will present some different outcomes using this new approach. The first outcome is some baby steps towards an analytic solution. Unfortunately, I will not be able to give you a full analytic solution today. The second outcome is, however, a very, very efficient numerical methods. So these numerical algorithms will severely outperform the previous ones and work much natural at strong coupling. And finally, by combining the first 2 points, I will present some new analytic results of the strong coupling spectrum. So let us jump straight into this new approach to the QSC. So to introduce the new approach, I think it's only fair that I first briefly recall what is the quantum spectral curve. So the QSC is a collection of functions. They're called Q functions. There are a whole bunch of them, 256, and they're all functions of one complex parameter, U, usually referred to as the spectral parameter. Now, among these Q functions, there's a set called P, which are particularly simple. They are simple because they have a simple analytic structure. So if I plot them in the spectral parameter plane, they're functions with only one cut. And so that's what I've been trying to illustrate here in my picture. Using my P's, I can construct another set of functions called Q. The way I can do this is through a finite difference equation. Usually we call this finite difference equation a Baxter equation. Now I have written down this equation here with some implicit coefficients. So let me just recall that all these coefficients are given in terms of the previously introduced P's. Now when you solve this equation, you can solve it requiring either that your functions are analytic in the upper half plane or in the lower half plane. And I have plotted these two different options here and added a little bit of a superscript with an arrow up or down, depending on where you find the ladder of branch cuts. Now what the QSC requires you to do is to take these functions and glue them together. So you take one function which is analytic in the upper half plane and one which is analytic in the lower, and you glue them together, and this gives you what we call a function with a long cut. And in this way, we have kind of restored some symmetry between the original P's and the Q's. So P has one cut, it's short, and Q, if you glue it together, also has one cut, but that cut is long. So this is the talk about the spectrum. So I also should tell you where we can find the spectrum. And the spectrum sits in the asymptotics of the Q functions. So once you find your Q functions, you can check their asymptotics, and you will find delta, the conformal dimension. You can also see that the asymptotics of P are fixed by the R symmetry charges, while Q depends on your charges of ADS space. At weak coupling, something easy happens, which is that the cut collapses. So instead of dealing with functions that have a cut, we can deal with functions that have a pole and other rational pieces. And this will give you a Q system or a quantum spectral curve for a rational spin chain. Now this makes our life a lot easier because it turns out we know quite a bit about rational spin chains. And so at weak coupling, we start from this rational spin chain, and then we start doing perturbation theory around it. So that's why we can essentially get analytic results at weak coupling. The way we do perturbation theory is that we usually introduce this Sokowski variable called x. And x is related to the spectral parameter for this x plus 1 over x equals u over g, where g is the coupling constant. And I've tried to depict a little bit how x here opens up the first cut for us. So this was at weak coupling. But the major point of this talk is to try to go to strong coupling. So the question is, how do we generalize the story to strong coupling? Well, you can start by this Laurent series that I wrote down before, and you can notice that at strong coupling it will reorganize itself very qualitatively in this kind of way. This poles at x plus minus 1, perhaps you can anticipate if you recall the structure of the quasi-momenta of the classical string. The issue here is that this sum is of course not well defined at x plus minus 1, and it turns out that the information contained at x plus minus 1 is absolutely crucial in order to get to the strong coupling regime. So to capture this information, I will introduce the key object for this talk, which I will call densities. Now these densities I've defined in the slide. The densities are raw, and they're simply a linear combination of p. So why do I call these object densities? Well, because if I integrate them on the unit circle, I can reconstruct my original p's. These densities have been defined with a very specific combination of p functions. So the question is, why pick this specific combination? So this is a bit of the tricky part of the construction. In no way is it a surprise that you can write this kind of density parameterization of Q functions. But what is interesting is that you can pick it in a very particular and nice way. So if we look and try to find some motivation from classical physics, you can realize that the combinations I picked here, if you were to just boldly replace your P with quasi-momenta, would be 0. Now, if you try to quantize this type of relation, you should consider what is known as a p-mu system, which is a system which I have unfortunately not written down for you. What this system will tell you is that at strong coupling, this combination of p functions will almost always be 0 as well, if you're on the unit circle, but it will not quite be 0 at x plus minus 1. And so what instead happens is essentially a picture like this. So here I've tried to plot this density, and you can see that it's sharply peaked at x plus minus 1. So we have defined some object which captures some important information, x plus minus 1, and essentially 0 everywhere else. Now we want to do exactly the same thing, but for the q's that I introduced and not for the p. But prefer that. Let's look at the density a little bit more closely. So here I have taken out the unit circle and I plotted it, so theta is just my angular variable. I can zoom in on one of these peaks, which I plotted now for a wide value of the coupling. And here comes the magic. So you can see that this density, it becomes more and more peaked as I increase the coupling. So I rescale my angular variable to take care about this fact. And then if I also rescale by entire density, it turns out that all these different curves look exactly the same. Now they're not quite the same. If you zoom in a little bit more, you can see that there is a slight change. So what's the main lesson from this? The main lesson is that if I try to take some strong coupling limit, these objects will go to some finite limiting shape. So it means that we can try to find this limiting shape and do perturbation theory around it. So we have some sort of object which we will try to perturb around to do analytic computations. And this is why we like these densities, because they behave nicely at strong coupling. So let's jump into Q. And for Q, you have to essentially go through a very similar derivation, but now you have to take into account the fact that these Q's were defined as functions with long cut. So I have here plotted them in the x-plane. I take Q1 and Q3. These are the functions that glue nicely together. Then I take the same functions, but I flip the arrow. Now this here is a combination of functions that will have a discontinuity on the real axis. But that discontinuity is also sharply peaked at x plus minus 1, mimicking the structure of my previous defined densities. I will call this density eta. And here is a plot of eta for another wide value of the coupling. And what will if you want to reconstruct your Q, you do once again an integral, this time an integral on the real line. And if you do the analysis, you will see that these densities also have a well-defined expansion as strong coupling. So it means that I can parameterize both my P and my Q function in terms of objects that have a well-defined limit as g goes to infinity. So this is the recap. By looking at these densities, I have objects which scales nicely at strong coupling, and if I can do perturbation theory around that, I have a good chance of finding analytic solutions at strong coupling. So in principle, the way you would do this is you will go back to the first equation I introduced, the Baxter equation. You will plug in this parametrization, you would solve those equations, you would fix the spectrum, and you would be done. Unfortunately, I have not been able to do this. And one of the main complications for not being able to do this analytically is that we don't know the leading order here. We don't know what the functions are actually in this limit. But instead of giving up, we should of course keep pushing. One idea would be to try to go back to other tools as strong coupling. And one of the very efficient tools here would be the asymptotic beta ansatz. But so far, I have nothing to say about this. And so we will push on instead to numerics. And so for numerics, I can indeed get the starting point because there has been very nice numerical work by previous people, which will give me a great starting point, albeit numerical. So let me move on and try to discuss some of the numerics results. So first, let me briefly outline how the numerical algorithm will work. So the main input is once again that these densities are sharply localized. And when I know this fact, I can take advantage of that and parameterize my function in a way that naturally takes this into account. And so I've written down such a parameterization here, which have some exponential p's outside, and then some complete set of polynomials so that I can parameterize any function. As I said before, if I have these functions and I impose Baxter, I am supposed to win and get the spectrum. So the next step of the algorithm is to impose Baxter. So you impose Baxter at a certain number of probe points. The usefulness is that these densities are sharply localized, so the probe points can be very close to x plus minus 1. So let's say someone gives you the C and D. Then you can use your Baxter equation to compute a new set of Q functions, QB, PB, on the real line using the Baxter equation. From these, you will be able to find new densities, which I call simply rho of B, and they're defined exactly as the original ones. Now, if someone gave you an actual solution of the QC, of course this new rho of B would be the same as the old one. But since we're doing numerics, we don't give an exact solution. And so the function that we find is not quite equal to the first one. So we have to do numerics to try to go to the correct point. So what we do is we minimize this error. This will give us a new set of C and D, and then we iterate. And as we do this, we will get closer and closer to the correct solution. Now, the amazing fact here is that when we do this, this becomes very, very efficient as strong coupling. Of course, the way it's presented here is very schematic, and the way to make it actually efficient is to take care in each and every step here and do a proper parameterization, find probe points that are actually useful. Nevertheless, here's the final result. So here's a plot of the spectrum. And this plot here starts from about g to the 2, something like this, and goes up to g100. Now previously, we would usually be stuck around g to 5. So this is a huge benefit of this algorithm, that we can get to insanely high values of g. Of course, there's nothing special about g100. It's just a good number, so when you get there, you feel internal satisfaction. But we can, of course, keep pushing it to, say, g200, 300. This will work very quickly. You can iterate with steps of g equals to 1, for example. Now, this beautiful plot also shows very nicely how we're interpolating between the spectrum of the rational spin chain, where we have this almost integer level-based difference in the conformal dimension. And when we go to strong coupling, you can see these sharp lines forming, which is telling you the string mass levels of string theory. So not only is this algorithm fast, it's also very, very precise. And when you have something precise, what you do is that you take the current benchmark result and you try to improve upon it. So before I showed you the value of the Konishi, which was currently known to 1 over lambda to 5 over 4. So let's try to improve this result. So to improve this result, I just want to recall briefly how we fix lambda. Sorry, delta. So here is a quick slide that shows you how to fix most terms of Konishi at strong coupling. So you use this very nice expansion of not delta, but rather delta square. And the first term here, which is multiplied by s and highlighted in teal, I suppose, you can all fix every coefficient here from Bassel's slope function. The next term, you can fix every coefficient from the curvature function. Then the numbers that are highlighted in olive can all be fixed by quasi-classics. All in all, there is only one term left to be fixed, which is this C3. So once you have this, you can expand it, and you will get the answer for any L for any S. So we took this, and we plugged it into the numerical algorithm, and we could find this expression. So I have written down the expression here in terms of actual zeta functions. Of course, numerics doesn't give you zeta functions, it gives you a lot of decimals. And so we simply sat down and we fitted until we found something that matched our accuracy. And also, we're of course guided by a little bit by simplicity here. As you can see that all the coefficients multiplying these zeta functions are very, very nice. And so we find this, which is in reality a numerical result, but it agrees with our numerics up to 10 to the minus 21, which is also the error of our fit. And once given this, we can plug it back in. And for example, for Konishi, we find this new correction. And so this is all good and well, but unfortunately it's maybe not that exciting, since the only thing we get is a new number. And what we would really like to understand is the actual analytic structure that arises at strong coupling. Luckily, we will find some cool clues if we just keep going and we keep looking at more complicated states. So here is a naive generalization of the kind of algorithm I use to fix Konishi. But for states which have mode number 2, or that is, they are belonging to the next string mass level. So I have highlighted here the first 3 numbers. The reason I've highlighted them is because they agree perfectly with our numerics. So we fully agree with this prediction. However, I have also encircled this 4th term, and that is for a good reason. So when we took our numerics and we fitted against this function, I fit a polynomial of, yeah, there should be L to the 4, of course, in the first term. I apologize. I find these results. And you can see that these numbers do not actually match. They're not that far away, but they're not the same. So what we tried instead is to make a slightly more relaxed fit, and we introduced additional inverse powers of the length. If we do this, all the numbers improve dramatically. So this seems to be a hint that this polynomial structure in L that we anticipated is actually wrong. Numerics is telling us that this is a structure that should appear when L goes to infinity, but should not be valid when L is finite. So how would you, in that case, figure out what to fit instead? So, of course, I've only written down 1 over L to the 4 here, but this will just keep going. This is an infinite series of correction in 1 over L squared. Well, to figure out something like this, we have to go back to the first point, which is the claim that I made that I can take some first step towards an analytic solution. So how do I approach this analytic solution? Well, I go back and I actually try to solve Baxter. And while we're still able to do this to any order, we can do it for some orders. And when we did this exercise, we found this quite remarkable result, which of course at first glance doesn't look that exciting. But when you know that you're missing some function to correctly fit the anomalous dimension, you get very excited because you get this unexpected square root here. So I have an additional square root of L4 minus 4L squared plus 36. And then you sit down and you try to fit against this function instead. And you realize that all the subleading coefficients are perfectly reproduced by expanding this function. And so when we took this and we put it into numerics, we could fit with respect to these, now L4, now L2, 1, and also the square root. And what the numerics told us is that if we do this, all coefficient multiplying these things are just simple rational numbers, except for the constant terms, which will contain precisely the zeta functions we expect. And so here is the result. And for good measure, I've written it down for delta squared. And I've also included one more order, because as soon as you realize what the basis is that you're supposed to fit, your life gets a lot easier, and you can start going even higher. And so here we have something that is truly new, in the sense that I hadn't seen these results before. And something that at least you can get excited about, some new analytic information. So when you see a square root, usually it means that there's two solutions. So a natural question is, what happens if I were to flip the sign in front of the square root? Well, if I were to flip the sign, I would expect to find another state in my spectrum. And so we checked, and we took numerics. And we found that we get perfectly the conformal dimension of another state, which is essentially a Laplacian of states in the SL2 sector. So if we can find both of these states, they're both in the spectrum, it is natural to speculate that this square root here is actually the effect of some sort of mixing. So as a proposal, let's say that these two states mix together. Well, in that case, there will be a 2x2 matrix. And that 2x2 matrix, when you compute the eigenvalues, will give rise to the square root. And so here is this 2x2 matrix that would give rise to this answer. And the obvious question, which I do not know the answer to, is, could you try to compute such a mixing from string theory? Is this something one could find using completely different methods? So with that, I think I've highlighted some of the more interesting things that we found. So let me go to conclusions. So what this talk was essentially about was about introducing these new densities. And the main point was that these densities had a finite limit as g goes to infinity. Using that fact, we could develop a numerical algorithm. And that numerical algorithm remains efficient at strong coupling, which was not possible with previous methods. And when we have that algorithm, we can gain high precision data and deduce new corrections to Konishi, but also find some new structure for other states. And this is, of course, a pattern that we expect to continue as we go to more and more complicated states, where we expect more and more severe mixing. Unfortunately, even going to the next trajectory, it's very difficult to even write down what the generalization of these square roots should be. But numerically, there should be no problem, and something that one would like to understand further. And so for the outlook, of course, the main task here is to still attack the analytic problem and find a way of deriving all these results without having to rely on numerics. And the missing ingredient seems to be that we can't fix these densities to leading order. So I think I mentioned already, we could try to use the asymptotic Bay ansatz, but perhaps we can get intuition from quasi-classical strings, maybe conformal Bootstrap, I'm not sure. Any approach, any idea is very welcome. Hopefully this mixing structure that we uncovered could be understood from some first principle derivation. And hopefully the results we have, the numerical results, will provide useful as input into other endeavors, such as Bootstrap, which I think would fit very well into the previous week's Bootstrap meets integrability kind of theme. And then, of course, there's always the standard questions and exercises, which is to take these methods and go down to ADS4, try to do it for maybe ADS3, see if that would in any ways help the situation we're at there. Or try to use it to see what we can learn about other objects such as 3-point functions. So that's it. So thank you very much for your attention.
Thank you.
Thank you. Thank you for the very nice talk. So I was wondering, one of the first signs that you have problems at strong coupling, when you start from the S matrix, Bethe-Ansatz, TBA sort of route before getting to the quantum spectral curve, is that the dressing factor has a bad expansion at strong coupling. It's only an asymptotic expansion, whereas
it is horrible.
perfectly nice at weak coupling instead.
Yes.
So these insight that you are getting, which you presented in terms of quantum spectral curve variable, can it be rephrased in terms of finding a better way to express the S matrix itself, or maybe change a little bit the asymptotic states to get something that is better behaved in such a way to have control, even in the usual, let's say, large volume, Bethe-Ansatz, TBA way of looking at things?
I think that's an absolutely excellent question. I haven't thought about it. It would be very cool if that could be used. I mean, naively from ABA, I don't see how to do it, since that would be destroyed anyways. But I suppose that if one can go to the TBA, where you make a much more explicit comparison with the dressing phase, yeah, then I hope if you expand it and you can try to read off what would be the contribution to the dressing phase, maybe there could be some very nice lessons to be learned. That's a good point.
Hi, thanks for your talk. The results look really cool. I was just curious about higher trajectories. I assume this means higher mode numbers.
Yes.
And so at higher mode numbers, you expect more states to mix, or do you have some hints about what are the general problems?
Yeah, I can redo this calculation for higher mode numbers.
Okay.
Unfortunately, Mathematica is not strong enough to give a nice answer. But
Right. And
yeah, exactly. We expect that there's 6 states that will be, and okay, you can easily say put L equals to 4, and you can find the different solutions. But I couldn't find a nice formula like this. So yeah, so for N equals to 3, you would expect 6 states to be mixing, for example.
right. Okay. Thanks.
It would be very cool to understand this for some KK tower or similar.
Sure. Yeah.
So the densities that you introduced, do you understand what they mean from the ABA point of view? Because they pick on the states that have very large worldsheet energy or momentum.
No, I'm not sure. Yeah, okay, Kolja has some speculation.
So my speculation is, which probably mad. Well, I mean, it kind of goes back to a paper with Volodya and Pedro about the SO5 model, where you can derive the Bethe-Ansatz by integrating out theta variables, which would correspond to longitudinal. Start from the Malochikov and then integrate out. But basically, so these densities would correspond to some degrees of freedom, which are reminds of longitudinal modes, I think, of the string. So maybe this is some kind of wave function of these 0 modes, which are longitudinal modes. And these are those which are very hard to kind of treat when people try to do from worldsheet point of view. Like there was a Jan and collaborators had the paper, and like really most of it was about this longitudinal mode, how you dissolve it, because all the rest is a flat space, but what is sensitive to the curvature is this longitudinal mode, because it spreads all over the idea space and actually builds the curvature. So all the rest is kind of easy to treat.
One last question.
But what was exactly this equation, what this rho 1 should satisfy? Did you show us? Or?
Well, I showed you very implicitly by saying that it should satisfy the Baxter equation. So that's the only thing we used. So you would start from your standard Q system and try to solve this. But of course, I suppose what you would like is some nice integral equation for this rho. And that equation, I think, a natural suggestion for how to get that equation would be to start from the p-mu system, which is essentially how I started by, I can It's unfortunately in the very, very first slides, but so the equation at the very bottom here, you can see that the left-hand side there will be the density. And then if I'm not being as so naive to claim that the right-hand side is 0, I would actually get an equation on the density. So that could be a possible integral equation to try to solve.
Let's thank Simon for a beautiful talk. And we move to Matthias.